looking at our last concept, which is biomechanics. So we'll start with our motion topic. So our key ideas are there. So linear, angular, general, speed, projectile, and looking at when forces come together. So we start off with the actual idea of motion. So motion involves an object changing position. As first mentioned, this happens with forces of some description must be applied. So types of motion. So we first have linear motion. So this is when all points in the body move in parallel lines that are either straight or curved. So all parts of the body travel exactly the same distance in the same direction at the same time. When a force is applied to that object, although it's the center of weight, the object will move in a straight line. So if we can see here, that linear notion there, that all our motion happens in this area there. So we move together in that parallel line. So we can see here the motion of the top of the head as a skier. We will go as that straight, as that linear, and then as a curved linear we can see like a jumper that might move in different areas. So even though that's curved, it's still a linear type of motion. You can see here even the linear nature of things moving. Alright. So angular motion or rotational motion refers to the motion of a body fixed around a point or an axis of rotation. So we can see here this example, here's our axis and the motion performs around there. Alright, so we can see that as we go around and around and around and around and around, it's around that axis hub. So it can be internal or external axis. So example, this gymnast on the parallel bars moves around that axis there, but also things like the rotation of a cyclist's crank is angular motion. So yeah. General motion. So this is a combination of the two. So for example, a girl in a wheelchair imparts linear motion to the rest of her body, but angular motion of the arms. This cyclist produces linear motion when they ride their bike, so they're moving in that parallel aspect, but they combine the movement with the angular motion of the hub there. So that's general motion. Alright, so what we're going to do quickly is have a look at a couple of YouTube clips and we'll describe the motion being produced in each clip. So first looking at this type of motion. We can see the skier moving a linear type. So we can see the ice skater here. So we have the linear motion here, and then we have angular motion with that triple axle around that internal axis. So we start with our linear motion as a ski jump as a result of the force of gravity, the slight push off to start with. As a result of the no rotation occurring, these forces can be concentric forces. At the bottom of the ski jump, we briefly experience the non-linear where they come down and up. Once airborne, the ski experienced that curved linear motion as a result of effective gravity. So with the ice skater, we start with the linear motion, the gliding over the ice. Then the spin is example of angular motion. So now we're looking at this idea of angular velocity. So this refers to the angle of displacement divided by time. So the angular velocity is an important aspect to understand the use of levers, which we'll look at as we move on. Projectile motion now is a very important concept. So projectile motion is the motion of bodies that have been projected in the air. So this occurs with considerable frequency in sport. Shot putters, golfers, basketballs, volley players will all have some sort of projectile, whether it's that person being the projectile or we have a projectile that has things acted on it. So when the body is projected, two things act on it, so gravity and air resistance. So gravity is the force that pulls projectiles back to Earth, so whether it's the ball or a body, and the air resistance will be something that affects the flight path. So that will be greater with a larger object, more surface area, or a light object. So three factors affect the horizontal distance of a projectile. So the angle of release, which is the first one, so the equal amount of horizontal and vertical force gives an angle of 45 degrees. So this ideal angle of projectile from ground level to cover maximum distance. Angles greater than 45 degrees result in shorter distances, greater heights and longer times of flight, and angles less than 45 degrees result in shorter distances, lower heights and shorter flight times. So for example, when a cricket ball is hit from ground level, at the optimum angle of release for greatest distance travelled is 45 degrees. So most other skill sports, there are other variables to take into consideration, such as spin. We also have height of release. So many sports involving the projectile are projecting an object from a given height above the ground level. So in most cases, the height of release varies between 1.8 and 2.4 metres above the ground. The following generalisations can be made about height of release: projectile angle and horizontal distance. So the greater the height of the release, the greater the distance, the horizontal distance it will cover, assuming that all force provided is the same. This means taller athletes have distinct advantage over shorter athletes when attempting to gain maximum horizontal distance. So as the height of release of the projectile increases, the optimum angle of release decreases. So if the release point is lower than the target, say for example a basketball shot, the release angle needs to be greater than 45 degrees. So also we have the speed of the release. So the higher the speed of the release, the greater the distance a projectile will carry. So the speed of the projectile at the release is far more important than the height or the angle of release in maximising the total distance travelled. So this is the reason why so many elite 100-metre sprinters also make good long jumpers. So for example, in the 80s and the 90s, Carl Lewis, who was a champion 100 metre, he had a very low angle of release, approximately 18 degrees, but the speed of the release was far greater than most other athletes. So we will do a practical looking at the height, angle and speed of release of projectiles, but in the meantime you need to go to topic 7.1 on pages 252 to 262, read and answer all the questions there. So moving on from there, 7.2 looks at speed and velocity. So when we're looking at speed, velocity and acceleration, when discussing the motion, other keys terminology can be discussed. So speed is defined as the distance travelled divided by the time taken. So, how far we move from one place to the other. Or velocity, which is very similar to speed. However, velocity incorporates direction. Therefore, velocity measures displacement. So distance and direction divided by time. So for example, in a 400-metre race, we can measure speed. However, we cannot measure velocity. This is because the 400-metre race starts and finishes at the same spot. So if we went for 400 metres from there and got displaced to there, we could measure the velocity because the object has been displaced starting there and finishing there. However, if we went around a 400-metre track, we can see because the athlete starts there and finishes there, the athlete actually hasn't been displaced. So speed, we could measure speed here, but no velocity, where here we can measure speed plus velocity. and they would be the same thing because the athlete or the projectile has been displaced. So, using that time, so distance divided by time, we could measure the velocity for those world record athletes in the following table, or the speed. There we go. Acceleration. So acceleration is a bit different. This is looking at the change in speed in a given time. So acceleration, meters per second, equals a change in velocity time taken. So acceleration could be both positive and negative. That is, that we can increase our velocity or we can decrease it. The following table looks at the changes in speed during Usain Bolt's world record breaking run in 2009. And we can see the changes in speed there. So from that initial point, the acceleration gets to 41.14 meters per second. And then over that next bit, we can see that even increases that acceleration there a bit. And then the deceleration as we get to the line. But the idea is from this starting point over the first 40 meters, he can look at the acceleration. And we'd use that in lots of sports to measure how, if an athlete would be better suited to a particular position because they can actually accelerate, faster than a different athlete. Okay, from here, what you need to do is go to pages 262 and to 264 and read and answer the questions about speed and velocity.